like Google Docs, you can pull the thing on the side, and it'll give you a thing that way.
Yes, let's get started. So today we're going to be talking more about the streaming model of computation. And so what sort of kind of analysis of data can we do in this? And we'll be looking at the frequency approximation problem today. This is kind of another kind of fairly kind of very basic model of the data representation, but I'll explain how this kind of has context lots of places. So something a number of people have used in their projects over the years in this course. Before we get started, I just want to look at the schedule. Fall break is next week, so no office hours or anything. Hopefully you all turned in the clustering homework. That wasn't, hopefully that wasn't too hard. Good. I think the scores for the first two homeworks and the feedback on the first two parts of the project are posted, so you should kind of know roughly where you stand. I think I did a pretty good job of not assigning you very much over fall break this semester. But when you get back, there'll be a frequency approximation kind of homework, and then the midterm test will be on Wednesday after you get back. Okay, so that will cover up through the clustering section, and optimistically we'll have it graded, but it depends on I don't know how busy the TA will be for grading over fall break or not. But at least you'll have finished that to get some grounded experience in that topic. All right, any questions so far? Yep. No, it does not have to be handwritten. You can do whatever you want to do it. Some people have basically, I don't want you using a magnifying glass to read it. Some people have like printed really small stuff on there. Eyeglasses are fine, but yeah, but it works best as a way to study when you go and you selectively choose what you think is the right material to put on there. You should be able to answer the test from memory if you understand everything well, but I don't want it to be a memorization-based test. I want it to test your understanding. And so I don't want that to get in the way. And I find this is a good way for students to force them to study for the test. Okay. Great. Okay, let's get into this topic. Okay, so we're doing this streaming model. And if you remember, yeah, question.
Will the topics in the Monday class before the exam be on the exam?
No, it'll only be up to the clustering part.
Only up to
yeah, so the streaming will be covered in the end term, which will be the second half.
Okay.
This is kind of about the right split point. Yeah. So a little bit more content in the second half than the first half, but yeah, and some of the concepts kind of build a little bit, so you can't forget about what you learned in the first half of the class. Hopefully you aren't forgetting all the stuff we've learned in here. Okay. All right, so we're starting with an input A, and this is kind of a stream of items, and so I write it in this. I like to use this pointy bracket notation. It's not like a n-wise inner product or anything, but there are going to be m items in the stream, and the things come in order, right? So I'm reading the stream one thing at a time, and you think of maybe dating back to your study of Turing machines or something, but I can only go forward in the stream, and while I have limited, the space here is limited, okay? And so I have limited memory to compute a summary as I'm sliding forward in the stream, right? And I can use what I had before at AI -1. I can use the old summary to update the new summary with the new data point. And the question is, what am I able to maintain in this model? And the idea is, let's say each AI will be in some universe of size U. And and I want to say that the space of or let me not do too fancy in this notation, but of M or U is too big. Okay, so I cannot store even one bit of information for every item in the stream, and I can't actually store the kind of the like I don't want to keep track of all the possible items. Okay, so think of this one as being all like IP addresses. So think of this as a piece of code. You're trying to do analysis of the data passing through a router, and the packets have IP addresses on them of where they're going to. And there are way too many IP addresses to keep track of something for all of them. And I can't keep track of all the packets passing through the router. Okay, so this paradigm, people first started studying this when kind of the internet was being born, and the routers were they wanted to figure out what could they study on the router when it had such limited space compared to the amount of data passing through it. But it has generalized to a lot of other settings where we have very big data, and we can't just do even linear space things or polynomial time algorithms more than super linear time algorithms on the data we have. We have to somehow be very efficient in how we handle it because of the scale. And this kind of generalizes to things where you might have multiple parallel processing or MapReduce, or to some extent GPU processing, where I want to do computation on something and retain a limited summary of that analysis and combine that with summaries from other analyses as well. A lot of these techniques that we'll be talking about carry over to these things, but this is the simplest model to study it in. So that's why we're focusing on that here. But a lot of these ideas really are show up all over the place, and when we really want to scale up the sort of algorithms we're considering. Okay, so our goal then in this setting is a summary that we can update with insertions. So when we read new data, so I only have to be able to add new data. Handling deletions is maybe something I can talk about in the lecture, one more lecture we get after break, or other models of that. And I need to be able to do small space, and that means I want the space to be some polynomial, usually hopefully linear, in log of m and log of u. Okay, and remember that log of m, this is, so like m is how many things we have, so this I can store a counter, and log of u is the space of all the items, so I can store a label that tells me which item is it in logarithmic in the number of items, right? I can, if I write out how many bits do I need to represent a number between 1 and u, I need log of u bits. Okay, so I can get an exponential saving in the space. I want algorithms that give me this exponential saving in the space. And this big drop is kind of a really big space improvement, and it makes it feasible. Algorithms that run roughly with space that depends on these, just how many counters and labels do I need, are things that I can run on a router and generalize to these other really large data sets. All right, so we talked about this a bit on Monday as well. So I'm going to be talking about the problem now we're looking at is the input specifically is each AI is in this domain U, and I want to think of the frequency. Well, let me make sure I do this consistent with my notes. the frequency, Fj, and this is for j in this set of all items 1 to u, is going to be the set of all AI in the stream such that AI is equal to j, the size of the set. Right? So if j stands for one of the IP addresses, how many packets do I see that is this destination as the IP address, the frequency of it, right? So e.g., how many packets with IP address j, right? So that's what this is capturing. Okay, so I'd like to understand kind of this frequency and kind of build an estimate of this, right? And so the trick again is there are too many different IP addresses to keep track of, so I can't possibly get the total count of all the different IP addresses I've seen. So there are a couple ways people have summarized this, and we'll talk about some of these. F0 is going to be the number of distinct so items. Okay, so this is the size of the Fj such that Fj is greater than 0. Okay, so the number of distinct different IP addresses I found, that's something that might be interesting to keep track of. F1 is equal to just the total number of items. So this is just equal to m, right? So the count of the stream, this is something we can easily maintain. And F2 is going to be, this is the sum over Fj squared, square root of this. Okay, so this will be typically actually what we look at here. Yeah, actually, yeah, this is the right way of writing it. Okay, so this is F2. This is kind of something tells us, so it's also a kind of a sense of a norm of how big is the stream, but the F2 will be much smaller than F1 if the stream is skewed, right? So if it has if the entropy of the stream is high, for instance, that there are some IP addresses that have a lot of traffic and some that have very few. And this is the case in practice. Most IP addresses don't see any packets at all. So they're both a matter of the scale, but typically F2 is much greater than F1. Okay. Sorry, I have this the other way around. F1 is typically much greater than F2. So F2 is typically much smaller. That means that the stream has a lot of skew. So this implies lots of skew. There are some very popular things and some not so popular things. Okay, and so, but we would, in what we're going to talk about today, and what we may, I think on Monday next week, I'll actually ask you what you want me to cover. We could talk about F0 estimation, something with respect to F2, or maybe how to handle things like deletions. But today we want to approximate the frequency for all values j. Okay, I want to get the frequency for all of the elements in the stream. Okay, this seems like it's not possible to do. Well, it's not possible to do exactly in full space, right? The total space I might need for this would be kind of linear in either M or U in order to do it exactly, but I'm going to do an approximation. So I'm going to do an approximate frequency. Okay, and I'm going to say Fj hat, which will have the property that the difference between Fj and Fj hat will be less than epsilon times m. Okay, and this will be true for all j in U. Okay, so I'm going to be able to store in a summary. So for all the frequencies, all of the different IP addresses, all the different words and tokens I'm keeping track of, or strings that I've seen in like on tweets, I want to keep an approximate frequency of them up to epsilon times m. Okay, and epsilon will be some number between 0 and 1. We'll think of epsilon as 0.01. So I want 1%. I want to be off by, say, 1% here. So I could say, okay, if the true percentage of this item was 7% of the time, it can be between 6 and 8% of the time. I would be okay with that. Okay? So what's going to happen is that, for instance, I can like round anything that's small, less than 1%, down to 0. This would be one way I could keep an approximation of all of the things if I'm allowed to round the small things down to 0. Okay. Okay, so how do you think, what's one tool we could use? We've already seen where I can keep track of the frequency in a stream. We've already seen one tool that we can solve this problem with. I want to do this epsilon m frequency approximation, get 1% error. Yep.
Do one of our sampling methods and keep track of see how many times.
Great. Great. So can we do sampling for frequency approximation? Okay. And so it turns out we can keep k equals, I'll let you guess this, samples in stream, and then we'll set fj hat, and we'll say that this set will be S, right? And so that will be the frequency will be the number of AI in S such that AI is equal to J. And I want to approximate the frequency of the full set. So I also, if I wrote this so it's keeping track of the count, I actually need to multiply this by m divided by k to scale it up. Okay. Okay, so the fraction of them would be this quantity divided by k, and then I want to estimate the total number I would have had. Sometimes it's easier just to think about the fraction that I see here, but just to map the notation, I'll scale it up this way. Okay, so and so my goal is to get that fj minus fj hat is less than epsilon m, and I'll say with probability greater than 1 minus delta for some delta is a probability of failure, right? So sometimes I'm outside the error bound sampling, I can get something unexpected. Okay, how many samples do you think I need for this? In terms of to get epsilon here. So it's going to be, I'm going to quantify this in terms of epsilon. It'll depend on delta, but the delta dependency will be very minor. So what is the dependency on epsilon I need for this? So if I want to get 1% error, about how many samples do you think I need to get? What? Just only one sample.
1%.
Oh, so I think I need 1% of all the data. Okay, so it's going to be better than this. It will not depend on m, the size of the data. So this will be great about samples. I can get the sample size to depend on epsilon, but not on the size of the data. So my data set actually could be infinite. I only need to keep track of a finite number of samples to get 1% error. Okay.
CLT central.
Yeah, okay. So what do you remember about these concentration results? What kind of bounds do you think I expect depend on epsilon? So turns out it's going to be roughly, write this in red, 1 over epsilon squared times log 1 over delta. Okay, so the log 1 over delta term is a pretty small factor here. I can set this to like 1/10 of 1%, and this is maybe like 10 or 20. But this term is important. This is going to be something like, if I want 1% error, this is going to be 10,000, right? So if I want 1/10 of 1% error, it's going to be going to be 10 million. Okay, so if I have epsilon equals 0, let's write this way, 1 over epsilon squared. So if this is 0.1, so 10% error, then this is 100. 0.01, this is 10,000, and 0.001, right? So 1/10 of 1% error, then this is going to be, got that in the wrong spot, 1 million. Okay, so it's not scaling. This is great. It does not depend on the size m. M can be kind of the number of, if I'm keeping track of all the different tweets I'm seeing, there's a huge number of tweets coming in. If I only want 1/10 of 1% error, I only need 1 million things to keep track of. That's not so bad. Okay, but this 1 over epsilon squared dependence, it turns out we can do much better than this. Okay. So we can do a sample with streaming. Streaming is kind of like a fairly universal approximator, but you can often do better. Okay, so let's see an example of how that and this works. This simultaneously holds for all frequencies, in fact. The frequencies that we don't see any estimates for, we're okay with the 0 estimator for. Okay, there's some, yeah, it was a big mathematical feat to kind of show that this works for all estimators, but this is possible to show. All right, so let's talk about better frequency approximation. And so we're gonna, and in fact, I only care about the really large. So one thing to keep in mind here, when I say I want all of them within epsilon, if I'm keeping track of these for these IP addresses, right? What I care about are the really frequent kind of IP addresses I see. I want to know if there's something getting 10% of the packets, that's probably because there's a distributed denial of service attack happening, where a lot of different kind of machines that have been compromised are trying to kind of take down some computer or network by sending it lots and lots of packets. And I want to catch it at the router so I can block it there before it goes and it takes over one of these machines. But that only occurs if I'm getting 5 or 10% of the traffic is when I can estimate it. I can detect this. So I'm okay with, say, 1% error. If I care if it's around 5 or 10%, I don't care if it's 6 or 7%. I know that's already sufficiently large. Okay, so I want to find these very heavy items. These are sometimes called the heavy hitters. So these are the really important items. And if you're keeping track of tokens in kind of a string of text, these are the tokens that are kind of occurring very frequently. And these are sometimes things you care a lot about, and you want to maybe pay special attention to. Sometimes they're stop words and you want to downweight them, but pay attention to things that happen after the stop words. Okay. So how do we do this in a stream? Well, I'm going to start with a simpler problem called majority. Okay, and so I want to solve this. I want to determine If there is some Fj that is greater than m over 2, then I want to output j. If not, I can output like anything. All right. So this is kind of like a very strange election that you have a bunch of candidates running, and if someone gets more than half the votes, they win the election. If no one gets more than half the votes, then it's kind of like a nihilistic thing, and could be a random person is elected. So maybe forcing people to build consensus very strongly. Okay. So how do I want to solve this majority problem. Okay, I want to use one counter and one label. Okay, we want to think about the counter and label way of thinking about this again, right? Remember, these are things like counter I can store in log m bits, and a label I can store in log u bits. These are both very small, and I want to use one of each. Okay, so how would I guarantee to solve this majority problem? If something is greater than half, then I have to output it. If not, then I don't care. But I want to detect if there was something that was greater than half the time. I have one counter and one label. How would I do this? What would an algorithm be? All right, there aren't a lot of possible algorithms here. So like, how should we initialize this?
You say you want code?
That's all I get. My space is really constrained. This is our warm-up exercise. We're getting only one counter and one label, but the problem we're trying to solve is kind of this fairly simple problem. I only care about things that are like, if the router sees over half the packets to one thing, I want to know about it.
You just choose a label uniformly.
Yeah, so let's think about running the sequence in order, right? So how would I do? So again, my input, the input is A1, A2, up to AI, ... Okay, so what do I do when I see AI? Yeah, so so initially I set the counter equals to 1 and the label equals to AI. All right, so A1 here. Yeah, so I made the same mistake as Linda McMahon, confused AI with A1. I don't know if you saw that. All right, that's our Secretary of Education. All right, so A1 here gets set to the first label, whatever IP address was in there. Okay, and now I need to update it. Now I have a for loop for I equals 2 to m. I'm going to, what should I do now?
At one, every time AI equals L.
Yeah, okay, so let's see. If AI is equal to the label, right? So this is one condition, right? It should depend on what the label is. I should read the label and decide what to do. Then I should increment the counter. Okay, great. So now I'm going to, okay, I saw another thing that I'm keeping track of. So now I'm incrementing the counter. Okay, what should I do if AI is, or else here? Else, I should do what? Okay, let's decrease the counter. C minus minus. So I saw something that didn't match. I'm going to decrease the counter. Okay, Is this enough?
Then, once you exit the for loop, if it's less than 0,
This algorithm can only keep track of A1. So I sometimes need to switch the label I'm paying attention to. So I still need to say, well, what if I keep seeing, I don't see it initially, but then I keep seeing the same IP address over and over again. Eventually, I want to switch the label to that IP address.
if
Yeah, let's do that. If C is equal to 0, then I change the label, and I think it's easier to analyze if I see C is less than 0. Okay, but then I set the label equals to AI.
what you then need to reset it.
Well, yeah, and then I will also, and in this case, I will set the counter equals to 1. Okay, right, and then at the end, okay, I'm out of the for loop. I'm just going to return the label. Okay, and I hope that if it was a majority, I got the right label at the end. If it wasn't a majority, well, then I can return whatever. Okay, I decided on the promises the algorithm would make based on what the algorithm will do. Basically what I can do with the algorithm. I can't guarantee anything with only one counter and one label if I don't have a majority. Okay, but I can argue that this algorithm with just one label and one counter, where I can just keep the count of whatever I think is the majority, is always going to end up with the right label at the end if there were a majority of that item. Yeah.
If they do not come in consecutively, and if they come like one after another, so that should not, like, start with 1 and the next one is not the same one, so it's going to be 0. They just like 18,
Yeah, this independent of the order. Let's say that I have a sequence, right? My actual input here is 3, 4, 2, 2, 2, 5, 2, 2, 6, 2, 3, 3, 2, 2. Okay, so the majority here is hopefully 2. 1, 2, 3, 4, 5, 6, 7, 8 in any order out of a total of 14 things, right? So this is over half. I should return with 2 in the label at the end. Okay. So what's going to happen is I'm going to put in 3, and then 4 is going to cancel out the 3. So I'm going to put my label down to 0 again. I'm going to put in the 2, right? My label is 0, it goes less than 0. So now I replace it, my counter is 1. Okay, now I see another 2, it goes up to 3, it goes up to 2, right? Let me kind of write the counters underneath here. So this will be the label, this will be the counter. So the label will be 3, counter will be 1, label will still be 3, but it's 0. Then after this, the label will be 2 and 1, 2 and 2, 2 and 3. And now it has to decrement. So it's 2 and 2, but now it goes up again, 2 and 3, 2 and 4, 2 and 3, 2 and 4, 2 and 2, 3, 2 and 2, 2 and 3, 2 and 4. And the important thing is the output here is 2, which is the majority.
What if in some case like 1 to 1? So both of those going to be.
So it always cancels out. Not both, they can't both be greater than half. They can both be exactly half, but only one of them can be strictly greater than half.
But in that case, it would be dangerous. Like,
yeah, this is kind of, there's no majority in this case, so I cannot put anything. Yeah.
Is it possible to design, and specifically for this pseudocode, an input that would make it to where it would output something wrong? Like, let's say the majority is still 2, and every other number, every other number is 2, but the first one is 1, and the next one, so it's 1, 2, 3, 2, 4, and it just keeps doing that. Would this pseudocode mess up?
Well, I never get a more than half of them being 2. If I only get the even ones being 2, that means if I start with 1, then I never get more than half as 2. So then I can output anything. If I ended with an odd number being 2, it will guarantee to output it. Okay? But basically everything that is not a 2 will get canceled out by something that's either not also a 2 or a 2, and I will still have some 2s left over because it's more than half. Yep. Yeah, I don't know for sure. I don't have a certificate on it. For this algorithm, okay, this is a warm-up. Okay. So because I can only use one counter and one label. Okay. Okay, so yeah, you're right. This algorithm by itself, doesn't seem that super useful, right? I can't know if it was useful or not. I don't have and if it's exactly M over 2, I don't guarantee anything, and there are lots of stuff that isn't quite super great about this. Okay, but easy to understand. I can do something here already. Okay, so how do I make this more interesting? So I want to do frequency approximation. And we'll describe what is called the Misra-Gries algorithm. And so this will instead use K counters. Okay, so now this will be C will be an array, and K labels. And it'll also be an array of labels. Okay? So now I can use K counters and K labels instead of just one, and now I can get something much more powerful here. Okay, and this will allow me to get this frequency approximation if I set K to be large enough. Okay. Okay, so I'm going to maintain these, and I'm going to, let me write down the algorithm here, but maybe you can kind of guess what you think the algorithm might be. Let's see, we're going to initialize init all C equals to 0, and all labels equals to just nothing, empty set. Okay, and so these will be unused labels. Okay, and now I'm going to say for I equals 1 to M. Okay, I'm going to say, okay, so first we'll say if there exists a Cj equal to AI, right? So I have a counter that matches the thing I'm seeing. So a label, sorry, I have a label. I have a label that matches the current input. Then I'm going to increment the associated counter. Makes sense? So if there's something I'm keeping track of, okay, and else, if there exists an label J which is empty, right? So I didn't have something that matched, but I have a label which is not being used, right? So it's not being used. Well, then I'm going to start using this label. So then I will make that label J equals to AI, and I'm going to set the counter J equals to 1, right? So this makes sense. So if I have an unused thing, then I will take over that label and I will set the counter to 1. If I have a label that matches one of the counters I already have, I increment this counter. Okay, so, but now I need to figure out, what do I do if all my labels are used, they're non-empty, and they don't match. And they don't match. What should I do now? Decrease for the smallest one, okay? Turns out this doesn't work because you can fill the first K-1 counters with two things, and then the rest of the stream is two new items that are alternating. And so that I keep decreasing that one thing, and I never recognize that I'm seeing a lot of things over and over again. So this just decreasing the smallest one does not work. We need to be more aggressive somehow. I can decrease all of them. Very good. So this is the critical step. There's another method that actually also works, but I will decrease all counters. Okay, so so for all j, minus minus. So I'm going to decrease all the counters. Okay. And so, and this is the whole algorithm. Yeah.
So that means since we can replace, that means we can replace if the count is 0 with a new label.
Yeah. So I have to say, if a counter is 0, yeah, if Cj equals 0, then label j equals empty set. Yes. So I can replace this by checking if any of the counters are 0 instead, but yeah.
What would happen if two counters both go to 0?
Then I would set them both to empty.
Both empty.
Yeah. Then I've lost the information. Yeah. All right. So to analyze this, we can actually say with K-1 counters and K-1 labels. Okay. And now so this will give me a frequency approximation guarantee. So how big do you think I need to set K in terms of epsilon? Epsilon, like to get 1% error. What? Yeah, that's right. So I can set K equals to 1 over epsilon. All right, so now I can get 1% error with the 100 counters, and 1/10 of 1% error with 1,000 counters. Much less than before. Okay, so why does this work? Right, what is the insight here? The key is to look at this operation. So how many times can I actually get to this state where I actually do this decrease all counters? How many times can I do that? Okay, so yeah, so like thinking globally, if I see m total items, how many times can I possibly call this?
But the pitch is what is happening?
Oh, every time the number of packets doubles?
So maybe the new package is half of the old received one.
If the new packet, the number of new packets is half of how many I've seen before. It's a little, so it will depend on K somehow. So it needs, as K gets bigger, I need to call this less often, right? Is the hope.
Is it M over K then?
Yeah, the total number of, that's exactly right. Yep. So the total number of times is M over K. And so, so why is this? Every time I call it, I'm decreasing the sum of all my counters by k minus 1 things. There are k minus 1 different items I'm subtracting the total count for. And the item AI I'm currently processing, I also don't put in a counter. So the total count is that I'm keeping track of is decreased by k every time I call this. And if there are only m total things, then I can't decrease the total count to less than 0. These always start at greater than 0, right? So so these never decrease to by something less than 0. So I can only call it m over k times. Otherwise, I would decrease some counter to less than 0. Okay, so if I can only do it this many times. Okay, so now what can I say about the frequency? So at the end, I will say fj hat is equal to cj prime if the label of j prime equals j, right? So otherwise, fj hat is going to be estimated 0. Okay, so for things where I do not have an associated label, I'm going to give their estimate at 0. Otherwise, I'm going to use this counter. Okay, so if I look at fj minus fj hat, can this ever be less than 0 for any j? Can this ever be smaller than 0? Can my estimate of something ever be larger than the true value? How would it? So if I don't have anything, I subtract 0, so that can't make it larger than the true value. And I can only, how can I increment the counter? Only if the label matches. And sometimes I miss it or I decrement the counters. So I can't ever be less than 0. Okay, so I can't overcount. I cannot overestimate on this. I can only underestimate, right? Because sometimes I decrease my counters when they shouldn't, when that's removing an actual count. But I need to do that to make sure I don't decrease too many times. Okay, and what's the most error that I can have? Yeah, if it was a counter I was keeping track of, I can only decrement it m over k times. Okay, so if it was something I was keeping track of, I couldn't have decremented more than m over k. And this is equal, if I set k equals 1 over epsilon, then this is epsilon times m as desired here. If I was not keeping track of it, right, so this is the guarantee I have. If I was not keeping track of it, and then either I would initiate a new counter if I could, or I would have to decrease all the counters, including this one, like a phantom counter, the kth one that I didn't actually keep here. So that one also can only happen m over k times, right? So even if either I was keeping track of it and then I can only decrement that many times, or even if I wasn't keeping track of it, that can't happen too many times either. So this gives an upper bound on how many times I can make this mistake. Okay, and so now I'm getting a much better much better error bound. Here, a much smaller space with the same error bound. The simple algorithm of just keeping track of these counters and labels. All right, so this is and you can't do any better than this. This is, you need at least this much space. If I have, so I'm only keeping track of, if I have 1% error, I'm only keeping track of 100 counters. Some of them need to be rounded to 0. So what happens if there are more than 100 things that have more than 1% frequency? How do I keep track of all of them? How can that work? Or more than 20 things that have more than 5% frequency. How could this algorithm possibly work then? Yeah, it's a trick question. Okay. There can't be more than 100 things that have 1% frequency, right? Because they all, then there would be more than 100% overall frequency, and this isn't possible, right? So if I, this kind of explains why if I needed to keep track of more than 100 things, I would need more than 100 labels. All right, so this is actually the size 1 over epsilon number of labels is kind of a lower bound here, because that's the most number of things I might need to keep track of that have at least 1% that's above the threshold. I can't round them down to 0. All right, so this is kind of a cool algorithm, one of my kind of favorite algorithms in the space. One thing this cannot do, at least cannot handle super well, although there's some work that kind of gets around this, and we have a new faculty starting next fall whose PhD thesis was kind of about this, but it's much more complicated than this. What if I have like a deletion? What if I'm keeping track of things, and so there's this idea of I'm keeping track of the people going into a stadium, and there's like a turnstile you go through, and it spins when someone goes in, and when you go out, it spins back the other way. What if I'm keeping track of how many people of a certain type have entered a stadium or some container, and then they can walk back out again? If I want to delete something in my counter, how would I do it with this algorithm? So I can maybe try and just take my counters and delete them or decrement them if I see a deletion. But my guarantees are, my analysis does not work so easily as before. So it's hard to say how this may or may not work with deletions here. So this algorithm does not naturally work with deletions. Okay, so I'm going to tell you a different algorithm now that's is totally different to solve the same problem, but can handle deletions very easily. And it's an example of a more powerful family of algorithms called these. It's going to be this algorithm is completely deterministic. What you actually store, what the counters are, depends on the order of the stream, but the guarantees does not depend on the order of the stream. Okay, the next algorithm I'll tell you, what is stored is not going to depend on the order of the stream at all. It'll store the same thing even if I scramble the order. What I store will be exactly the same, but it's going to be a randomized algorithm. Okay, and it's going to handle deletions. Okay, so Misra-Gries, okay, it's going to let's just say trouble with deletions. Turns out if you have a bounded number of deletions, it's probably okay, but and then it changes the state, although not the guarantees, if the order of the stream changes. And this is going to be deterministic. Okay, and the error is going to be less than or equals to epsilon m. Okay, there's going to be another algorithm we'll describe next. That's going to be called the count min sketch. The count min sketch will handle deletions in the called the turnstile model. So I can only delete something that was already inserted. Okay. The state is the same with changed order. Okay, it's going to be randomized. And it's going to have the same guarantee. It's also going to have less than epsilon m error. In fact, the error here is going to be that, in fact, if I say this a little bit more carefully, this one will have 0 less than fj minus fj hat, less than epsilon m. This one will have the other way. It'll have 0 less than fj hat minus fj less than epsilon m. Okay, so it's this one's going to give an undercount, and this is going to give an overcount. So it's always going to overestimate the quantity, but not by too much. Okay, so let's see how we do this algorithm. The count min sketch. Yeah, there's maybe, okay, maybe I'll come back at the end and say that. But the count min sketch. Okay, this one I'm going to have. So instead of labels, I'm going to have an array. Okay, I'm going to have a k by t array of counters. So this will be counter C1, 1, 1, 1, 2, up to C1K. This will be C21, C22, CT1, CT2, CTK. Right, so I'm going to have an array of counters. Okay, I'm also going to have, so I'm going to have K times T counters. I'm going to have K is going to be set to 2 divided by epsilon, and T is going to be equal to log of 1 over delta. This will be handle my probability of failure. This will be kind of, I need at least 1 over epsilon of these counters. Okay. I'm also going to have T hash functions. Okay, so Hj will be drawn randomly from a family of hash functions, and Hj will go from the set of items I have to something between 1 and k. So I'm going to map from the set of all IP addresses to one of the k columns here. I'm going to have T of these hash functions, right? So I'm going to think of H1, H2, up to HT, right? And so how it'll work is that this hash function will index into some counter H to kind of J prime. It's going to somehow when I see an item, it's going to tell me to go to one of these counters. And I'm going to have T of these hash functions. Okay. And the algorithm now is going to 0. I'm going to set and it's it's going to be a uniform hash function, right? It's set Cij equal to 0 for all ij, right? So for all of these, I'm going to go to 0. Let's not use Lj. Okay, so now for I equals 1 to m, for j equals 1 to t. So for each of the hash functions, I'm going to do this operation. So hash function j h of the jth hash function ai, this is going to get, I'm going to increment this hash function. Okay, so this is my algorithm here. Okay, so for each item in the stream, I'm then going to cycle through each of the hash functions. I'm going to figure out where it indexes into here, and I'm going to increment this counter. So every time I see something, I only increment the counters. Okay, and then I'm going to create my fj hat is going to be, yeah, so how do I think I create, yeah, so this is the algorithm. How do I create my fj hat estimate, right? So now I've run through the stream, I've incremented a bunch of the counters in here. They started all at 0. When I saw something, I added something. Now I need to create an estimate. The certain IP address, the jth IP address, I want to figure out how many things do I think were there? How do I get an estimate out of this array of counters?
J divided by C.
C, what is C?
So
Divide by, so yeah, I want to get an estimate. Let me write that more clearly. C L J. Yeah. So I want to get. So I want to get an estimate of how many things times I saw that jth IP address. So I'm not looking at the fraction, so I'm not going to divide by m here. But I want to somehow figure out, like, let's say I look at the second hash function for the IP address j, and I'll go and find one of the counters. Right? So I can do that. I can say for hash function j, this is, let me say instead of j here, let me call this something else. For a query IP address, right, for q in u, so I can look at hash function j, and I can look at the jth hash function, and I'm going to hash the query into here. So I'm going to go and find this counter. Okay? So this will give me some estimate of the count, right? But I've only used one of the t hash functions. I want to somehow use more than just one. I could just pick one and return it and hope it's a good estimate. So I could take the average. That's what you're suggesting. So suggesting the average here, 1 over t. So it turns out it's hard to say something about the average because I might have some other very big event, some other IP address that was one of these heavy hitters that collided with this one. So it always lands here also. And the one I want to estimate. And so this one IP address is going to pull the average really high up. So the average is kind of susceptible to these things. So the average won't work well. Actually, the average isn't going to work well. What's another option other than the average? Do the median, okay? The median of these, okay? So it turns out the median will be what we'll use for something called the count sketch, which I could maybe do on after break. Talk about that. And that has other guarantees that actually map with the F2 frequency. So if the data is skewed, this actually works better. The median is not the best thing I can do here. I think the median, you can actually get some bound here that will work, but I can do something smarter than the median. No. Okay. It could very likely they're all going to be different. So the mode won't tell me anything. Yeah, kind of cycling through your options here. Let's go back. Well, what was the name of this sketch again? The minimum. Oh, okay. Why would I want to pick the minimum? Can these counters ever be too small? Can they ever be smaller than the true value? Is it possible for a counter to be, every time I see an item, this jth IP address, I always increment all of the associated counters, right? I do it for every hash function, I increment the counter, right? So what I'm going to do is the min over j in u, because each of the counters is an overestimate. It overestimates when there's a collision with another item, also increments that counter. So they're always overestimates. So why don't I just take the smallest one? That one will by default be the least overestimate. Okay? Yeah, so the min is a very kind of aggressive thing to do here. Take the minimum, because I know they're all overestimates, so I might as well take the smallest one. So that's why it's called the count min sketch. Yeah. All right, yeah, so this is the algorithm, and it will have the guarantee that FQ hat minus FQ is always less than 0, so it's always still an overestimate. It can't, even though I took the minimum, it can't be too large, it can't be too small, and it's less than epsilon m with probability 1 minus delta, because I have log 1 over delta. So each of the probability that each of these will have more than epsilon m error is going to be 1/2, and I'm going to take the union bound over log of 1 over delta of them. Log base 2, 1 over delta, and this will work out. All right, so we have about 10 minutes left. Can either two options, or probably 3 options here. I can go through the analysis for this. It'll take about 10 minutes. It's not too hard. It's also in the notes. I could go through the count sketch, which uses the median and gets kind of a different bound based on L2, and is kind of like this, but has a twist where it also sometimes subtracts things and then undoes that subtraction. Or I can talk about the A-Priori algorithm, which was around the turn of the century, they thought was one of the 10 best algorithms like in data mining. And it's something, if you look on ACM list of what you should teach in a data mining class, is listed there, but I don't think it works very well. But maybe I should cover it to adhere to ACM guidelines. But it's this famous thing, if you've heard that, this association mining, if you like, someone goes to the store and they buy beer, they're also likely to buy diapers. If you've ever heard of that, that comes from this algorithm, which turns out is not true, but it's some useful ideas in it. So who wants the analysis? Okay, it's who wants the count sketch? Who wants to learn why you might buy diapers if you also buy beer? Okay. All right. All right. Okay. Great. I guess I sold that. Okay. So let's talk about the A-Priori algorithm. This is called A-Priori algorithm. Okay, and this is a setup that's similar to what we talked about, but is a little bit different. And so here now we're going to get a stream, and in fact we don't need it's not even a stream of items, but you're going to get a set of sets of items. Okay, so I'm going to have some domain U, and this is often called like market basket analysis. So think of all the things you could buy at the grocery store. So if you ever work, grocery store has data scientists working for them, Harmons or Smiths, and they have a long list of all the things they sell in the store. That's what U is. And when someone goes and has a receipt, you have so it's called market basket analysis. And so this is kind of U is all items in the store. And then I'm going to get these receipts R1, which is going to be A1, A2, let's just write down some numbers. I have a made up example here. 1, 2, 3, 4, 5. This is kind of all the items which showed up on this person's receipt. They bought 5 items. Not some big spenders here, but or at least not a grocery store, but quick trips for smaller example in class. 1, 3, 5, 6. Let me just write these down. 2, 6, 9, 7, 8. 1, 2, 6. 0, 3, 5, 6. 0, 2, 4. 2, 4. Let me write some more up here. 6, 7, 9. 3, 6, 9, and 6, 7, 8. Okay, so these are all the receipts that came through in a day. And I want to find what items were often bought at the same time, right? And this would be like if I put beer on display, then I should put the diapers right next to it and maybe price the diapers up because they'll probably buy them if they're picking up some beer. Okay, this is the idea behind it, but I want to find what are the associations here? What are the things that often occur commonly at the same time? Okay, so I'm not necessarily doing this in a stream, but it's also I'm finding the high frequency sets of items, not just the high frequency items themselves. But the first pass of this, again, okay, the first pass is I just want to compute the total frequency of all the items. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And I want to count how many times each of these occurs. Okay, so how many 1s do I have? 1, 2, 3. How many 2s do I have? 1, 2, 3, 4, 5, 5 2s. Okay, you guys can help me out here. How many 3s do I have? 3 of them. No, I think 4. 4 3s. Okay, how many 4s do I have?
3.
3 of them. Okay. I think. Yep, that seems right. How many 5s do I have? 3. How many 6s? A lot of 6s, right? Should have 8. 1, 2, 3, 4, 5, 6, 7, 8. This is a 6. It's kind of written over. Okay, so 8. How many 7s do I have? 4. How many 8s? I should have 2. And 9s, I should have 4. This is 6, 7, 8.
The very bottom.
2, 4. 2, 4. Okay. Okay. So now I want to say, I want to find things that I want to only keep track of if things are going to be bought together a lot. Well, those can only be things that are individually bought a lot, right? If there's some really rare products, some really kind of fancy spice that isn't sold very often, that's not going to be one of the big associations probably. So I want to only keep track of the things which are very frequent, so appear at least 4 times, so at least 1/3 of them. Okay, so the 2, the 3, the 5, the 6, the 7, and the 9, those are the only frequent items. These are the frequent items. Well, in this case, not 5. Okay. How do I don't know how to undo the highlight. Okay. 5, 3. Okay. Only items occur more than 1/3 of time. Okay. So I'm only going to keep I only need, if I want to find pairs or triples that occur more than 1/3 of the time, or some fraction of the time, well, that means that individual items have to occur more than one fraction of the time. So I first keep track of the first pass to just the individual frequencies. And then I can go and say, well, now let me go look at only the pairs among these items. So 2, 3, 2, 7, 2, 9, 3, 3, 7, 3, 9, and I forgot 6. Somehow my 6 got erased. Okay, let me try this again. 2, 6, 2, 7, 2, 9, 3, 6, 3, 7, 3, 9. I run out of space. Well, the full matrix can be very sparse, right? So I mean, I could write it this way, but what you think of is keeping track of the pairs of things. And hopefully this list is not too long. And the idea is I've thinned out the list in the first step. Okay. Okay, and then I have 6, 7. Oh, I still run out of space, but okay. This list is not supposed to be too long. Okay, let me try this. Let me just try writing it again.
Will we also go to 2? Will we also go to pairs of 3?
Yeah, we'll go to pairs of 3, but only if we have some tuples that are common. So I kind of thin out as I go. 3, 7, 3, 9, 6, 7, 6, 9, and 7, 9. Okay, good. So now I can keep counts for each of these. Okay, so I want to count for how many times do 2 and 3 occur together. For instance, here's an instance where 2 and 3 has occurred together. Is this the only time? Okay, so once, 2 and 6, twice, 2 and 7, once, 2 and 9, I think twice, 3 and 6, 3 times, 3 and 7, 0 times, 3 and 1, 9 once, 6 and 7, 3 times, 6 and 9, 4 times, and 7 and 9 twice. Okay, so now if I only wanted to keep track of things that occurred more than 1/3 of the time, that means they would have to be at least 4 times here. And the only instance where this occurs is with items when I have items 6 and 9 are the only time that occurred more than 1/3 of the time. If I set the threshold lower to be 1/4 of the time, I would have had to have a lot more tuples here. And then maybe I would have found 6 and 7. But I cared about 1/3 of the time was my threshold. And that meant that only 6 and 9 occurred here. Okay, so could there be any triples now? There can't be any triples because it would need to be 6 and 9 and something else. And that something else did not occur more than 4 times with either 6 or with 9. So I can kind of filter as I go. And typically the second round or maybe the third round is the biggest expansion. And then it gets smaller and smaller down. And so this is also useful in searching for like for cliques and graphs. I find all the degrees that the edges in the graph, then I look for all triangles, and then I look from the triangles to see if they can make a fourth thing. And so this a priori algorithm kind of filters by the frequency and then the doubles and then the triples. This sort of implication and inference you draw from this tend not to be super significant because there's lots of multiple hypothesis testing and it's not very stable under sampling. So if you recollect the data, you might get fairly different results here. So this isn't used too much in like downstream analysis, but this idea of pruning by first filtering out by the frequency and then the doubles is kind of a clever idea here. All right, we'll stop and then I'll cover some potpourri about stuff. Do you want to learn about like deletions and stuff and when you have decaying things, or do you want to learn like more different sorts of sketches like for distributions and on after break? Or I can choose.
Put a poll on Canvas.
Yeah.
Okay, I'll put up a poll on Canvas. Okay. Oh, there's lots you can do in Canvas. You would be surprised. It's kind of clunky, but it's a lot of stuff built into it.